Fine. So in the last lecture on Monday, I guess, we started the discussion of deadlock. And firstly, we discuss principles of deadlock. Again, one more time, let me remind you that this is a typo. Then we discussed different strategies, right? We started with deadlock prevention. So I hope you remember what is the idea behind deadlock prevention? Can anyone tell me in brief? What is the idea behind deadlock prevention technique? If you remember. Yes? Anyone? What is the technique, deadlock prevention technique? What we actually try to achieve there? No one? So let me remind you, for deadlock, for deadlock, there are four conditions. For deadlock to occur, there are four conditions. Okay, can you tell me what are those four conditions? Guys, are you there or you have just logged in? What's the case? Mutual exclusion should not, mutual exclusion must be there. That is one condition. Second,
No preemption.
no preemption, hold and wait. Correct. These are the three necessary conditions: mutual exclusion, hold and wait, and no preemption. These are the three necessary condition. And the fourth sufficient condition is circular wait, right? And in deadlock prevention, we try to make sure that none of these four conditions occur at once. If we can avoid at least one of them, then there will not be any deadlock. So this is how we can prevent deadlock. But then we discuss that what are the problems with this technique, right? As a general technique, we cannot use deadlock prevention because it has its own disadvantages, especially it is not efficient. For example, mutual exclusion, you cannot avoid mutual exclusion. It has to be there. Otherwise, your resources must be in corrupt state, can be in corrupt state rather. Then for hold and wait, how you can avoid hold and wait? There are few ways, but those are the inefficient ways. Then non-preemption, you can achieve non-preemption, but it does not work in all the cases. And then circular wait, again, if you want to avoid circular wait, then whatever ways you can adopt for that, they are again inefficient. So all in all, deadlock prevention is not an efficient technique. That is how we discuss it. Then we talk about deadlock avoidance. In deadlock avoidance, basically what we try to do, we try to find out at a given point, whatever state is there. And if some request comes, you assume that if I grant this request, whatever state will be achieved, will that be a safe state or unsafe state? If it is going to be a safe state, then you grant that request and go further. Okay. But if it is unsafe state, then you don't allow that request to be granted. And in that case, basically what we try to do here, when we find that after granting particular request, it is going to be an unsafe state, it does not mean that deadlock will occur, right? There is no such guarantee that deadlock will occur if it is proceeding further from this unsafe state. But there is a potential deadlock if you proceed further from that unsafe state. So just to avoid that potential deadlock, we make sure that we do not allow a request which takes your system into the unsafe state. So that was the idea of deadlock avoidance, and that is what we discuss, right, with the help of this different vectors and matrices. And then we discuss this algorithm also, right? Simple algorithm is there. So that is how that up to that point we discussed in the last lecture. Now next, what are the advantages of this deadlock avoidance technique? So in that case, it is not necessary to preempt and roll back processes as in deadlock detection. Though we haven't discussed about deadlock detection, which is the it is a technique that we are going to discuss just after this. In that technique, you may need to preempt and roll back processes, which is not the case with deadlock avoidance. Okay. because it is a kind of proactive technique. Like before you get into the deadlock situation, it is trying to avoid that. And this technique, deadlock avoidance, it is less restrictive than deadlock prevention, because in deadlock prevention you make sure that not all those four conditions occur at the same time. That is how you are trying to achieve deadlock prevention, and in that case it becomes more restrictive. So this technique, deadlock avoidance, is somewhere between deadlock prevention and deadlock detection. Okay, but what are the restrictions? If you use deadlock avoidance, then what are the restrictions? So of course there are few assumptions we had when we discuss this deadlock avoidance. For example, maximum resource requirement must be stated in advance. That is a claim matrix. I hope you remember claim matrix, where you need to give what is your maximum resource requirement for each type of resource in advance before you start. Processes under consideration must be independent and with no synchronization requirement. So when you have these processes for which you are trying to find out whether there can be a potential deadlock or not, you need to make sure that they are independent and there is no synchronization requirement between those processes. It means there should not be any, no process should be waiting on another process to do something. That kind of synchronization should not be there. So that is another restriction. There must be a fixed number of resources to allocate. And of course, that is another restriction, that fixed number of resources must be there to allocate to the process, and no process may exit while holding resources. So if some process is currently holding some resource, it cannot exit, though it is not under control of the user control. It is not under user's control, but that is required. So OS needs to be designed that way, that if any process is exiting, it is being killed or whatever the result, it is being crashed, whatever the possibility, make sure that that resource is not there with that process. So these are few restrictions which are applicable if you want to use deadlock avoidance strategy. But again, these restrictions are not practical every time. So there is one example regarding deadlock avoidance. Okay, so let us very quickly discuss this. Assume that there are 5 processes, P0 through P4, and 4 types of resources are there. And at time 0, we have the following system state. Okay, so maximum instances of resource type A, that is 3. Out of that, 2 is allocated and 1 is available. So this is the just a statement. And if I put this statement in this form, okay, if I put it in this form, this max matrix is nothing but claim matrix. This max matrix, because in other literature it is known as max matrix. So you can see that this is allocated resources. So that's why this is allocation matrix. There are 5 processes and 4 resource types. And this is the claim matrix, and this is the available matrix. So what you need to find, so this is your problem statement. I have converted this problem statement, okay, into this form. So this is your current state at time 0. So what we need to find at this point, first of all, what is our algorithm? This is same thing that we discussed in the last lecture. You have C, this is claim matrix, this is allocation matrix, and this is available matrix or available vector, because it is only one row. This is V, this is C, and this is A. So what we need to find? First of all, you need to create need matrix. Need matrix, that is nothing but claim minus allocation or max minus allocation. So this is your need matrix. This is your need matrix, and this is your available vector. Okay, so can you complete any process with that available resources? That is the first job that you need to do. With this available resources, can you complete any of these processes? So that is Banker's algorithm. So use the safety algorithm to test if the system is in a safe state or not. And for that, we will first define work and finish. So initially work, that is nothing but available resources, and finish is false for all process. Okay, let us not get into this terminology, because these are the terminology that I might have used from some other literature. So don't worry about that. But you can see like this, that this is my current available resources, and currently I haven't marked any process because I need to find out, can I mark all these processes true, okay, one by one, so that it will be in a safe state. So if you see that, now what is the requirement of P0? What is the requirement of P0? 0100. Can I complete this requirement with the help of this available matrix? What is requirement? 0100. I require only one resource of type B for P0 to complete. Can I complete that with this? Yes or no? Can I complete or not? Okay, I assume that you people have just logged in and you are not present in the class. That is what I assume. I guess you people don't value your time as well as others' time. And that is very ridiculous. And it is not going to help you anymore in your life. Fine, I am least concerned about your attitude. So let me finish my job, what I am doing here. Fine. So in that case, you can go through this example by your own. I'll share this slide. No problem. And today, let me finish my lecture as soon as possible so that you can get your free time. Deadlock detection is the next strategy. We have seen two strategies, deadlock prevention and deadlock avoidance. And next is the deadlock detection. What this detection strategy does. So deadlock prevention strategies are very conservative. That is what we discuss. It limits access to resources and impose restrictions on processes just by making sure that none of all those four processes, I mean, not all four conditions become true at the same time. And deadlock detection strategies do the opposite to that prevention. It just allows deadlock to happen if it is going to happen. Okay, so for that, what it does, resource requests are granted whenever possible. It just sees that whatever request comes for particular resource, it just sees that with current available resources, can I complete this request? Yes, grant it. Doesn't bother about what will happen in future. So in this strategy, you don't bother what will happen in future. You are not, you are least concerned about safe state, unsafe state, and all those things. Okay. So in that case, in this detection strategy, resource requests are granted whenever possible. But then what this system does, it regularly checks for the deadlock. It just check out, is there any deadlock right now? So for that, again, a very similar matrix we will use an allocation matrix and available vector. As previous, we have done it in deadlock avoidance. Similarly to that, we have allocation matrix and available vector. Now also uses a request matrix queue now. Now this is different from the deadlock avoidance strategy, where Qij indicates that an amount of resource J is requested by process I. Okay, so that is the request matrix. And the algorithm proceeds by making processes that are not deadlocked. Okay, the algorithm proceeds by marking processes that are not deadlocked. So initially all processes are unmarked. You assume that all processes are deadlocked, but one by one you try to mark those processes which are not in deadlock. And if at the end you are left with some unmarked processes, it means those processes are in deadlock. But if you left with no unmarked processes, it means all processes are marked. It means there is no deadlock. So this is deadlock detection. Okay. So what is the algorithm? Mark each process that has a row in the allocation matrix of all zeros. Okay. So you just find out any process if it is not allocated any resources. So if process is not allocated any resources, it cannot be in deadlock because it is not blocking anyone's request. So you just mark that process, it cannot be a deadlock process. Initialize a temporary vector W to equal the available vector. So now you just store value of available vector into W variable because we are going to update it. And find an index I such that process I is currently unmarked, and the ith row of Q, because Q is a request matrix, each row of this Q, it it is representing request of different resources for particular process. So find out some process I, okay, and then see the ith row of Q. If it is less than or equal to W, it means if that process request can be completed with the available vector W, because available vector we have stored in W, right? So if it can be completed with the available resources, it means if Qik less than or equal to Wk, for K which is in between 1 and M, that is K represent the index of resource. If no such row is found, terminate the algorithm. If you can't find any process which can be completed with the available resources, just terminate the algorithm. And after termination of algorithm, we will check. But before that, if such a row is found, mark that process I and add the corresponding row of the allocation matrix to W. So what you need to do, if you can complete any process with the available vector, then you assume that I will grant these resources and this process is completed. Just assume that. And with that assumption, now what you need to do, similar to the previous algorithm, whatever resources are allocated currently to that process, you just get that resources back, add it into the available W, okay, and your W will be updated accordingly, and you find the next process which can be completed with that updated W. So these are the 4 steps. A deadlock exists if and only if there are unmarked processes at the end. So after completion of this algorithm, if there is any unmarked processes, it means it is a deadlock. And each unmarked process, it is in the deadlock condition. So this is the example. So you can see that this is my allocation matrix. Currently P1 is allocated this resources from R1 to R5. One instance of R1, one instance of R3, and so on. So that is allocation matrix. This is our resource vector. This is our resource vector. That is nothing but our available vector. This is our total resource vector. So total 2 units of R1 is available, total 1 unit of R2 is available, and so on. And this is available vector. This is not allocation vector, this is available vector. So again, there is a mistake in the typing. This is available vector. Now, this is interesting. This is different. This is request matrix. And request matrix is nothing but, you can see that P1 still needs 1 unit of R2 and 1 unit of R5. P2 still needs 1 unit of R3 and 1 unit of R5. So that is a request matrix. So let us follow algorithm. First of all, we will mark P4. Now, if you see P4, as it is not allocated any resources, it cannot be a part of deadlock processes because it is not using any resource. Though it wants some resource in future, but currently it is not holding any resource. It means this cannot be a part of deadlock. So just mark P4 because P4 has no allocated resources. Okay. And then set W equal to available vector. So just use one temporary variable W with the available vector. Now P4 is already marked. So we are left with 3 more processes, P1, P2, P3. Okay. Do we have any out of these 3? Do we have any request row for any of these 3 processes which can be completed with W? If you see, can we complete P1 with this W, with this available resources? No, it cannot be, right? Because it requires R2, which we don't have. Similarly, P2 requires R3, which we don't have, but P3 can be completed. Yes, P3 can be completed. So the request of process P3, it is less than the or equal to W. Yes, so mark P3. Just mark this P3. And whatever is allocated to P3, that will be considered as freed resource. You just add it into the W. So if you add it into the W, W will become 00011. So you have 1 unit of R4 and 1 unit of R5 free with you. Now with this new available vector, can you complete any of P1 or P2, which are the left processes, which are still unmarked? Can you complete any of P1 or P2? It is not possible. If you see the request matrix, it is not possible to complete P1 because it requires R2 unit, and P2 cannot be completed because it requires R3 unit, and we don't have any 1 unit of this. So no other unmarked process has a row in queue that is less than or equal to W. Therefore, terminate the algorithm. Now you cannot find a such process, so terminate the algorithm. And after terminating algorithm, you can conclude that P1 and P2, they are still unmarked, indicating that these processes are deadlock. Okay. So as after the algorithm terminates, you can see that P1 and P2 are still unmarked. So it means these are the deadlock processes. So this is what is all about deadlock detection. But how it helps? Just by finding that there is a deadlock in the system and these are the processes which are part of deadlock, how it is going to help us. Okay, our job is to make sure that there is no deadlock. And what we are doing, we are allowing process to get into the deadlock, and after that we are detecting. But how it helps? So of course there is some recovery strategy. Okay, if deadlock is detected, then do some recovery strategy. And what are those recovery strategy? Abort all deadlock processes, whichever processes are in deadlock, just abort those processes. That is one thing. And back up each deadlock process to some previously defined checkpoint and restart all processes. So when you abort this process which are in deadlock state, you take them to the some previous state which was the checkpoint. I hope you know meaning of checkpoint, which might be you might have heard this term in database subject. Okay, so whatever was the last save point or the last saved point, that is called checkpoint. You take that process back to that. Basically it's a rollback. Okay, and then you restart that process. So when you are aborting any deadlock process, you make sure that it is rolling back to its previous checkpoint, and then you restart that process. When you do so, there is still chance that again in future there can be a deadlock, because we are granting process request if it is possible with the available resources. So again there is a chance that in future also deadlock can occur, but practically it is observed that deadlock do not occur as frequent as we are thinking about, right? Because it takes very specific a very specific sequence of execution of processes so that processes become deadlock, and it is not happening very frequently. It is very rare condition. So that is why we prefer deadlock detection and recovery. We allow, if deadlock is going to happen, we allow that, we check that, okay, we detect that, and finally we roll back the process. That is the best strategy in that sense. So successfully abort deadlock processes until deadlock no longer exists. So you need to take all those processes one by one, take one process at a time, abort that, roll back it to the checkpoint and restart that. And just by aborting only one process, if it is possible that your deadlock is broken, your deadlock is solved, then you don't need to abort all other processes, because what is our purpose? Just to break this deadlock situation. And when you abort any process successfully, you need to preempt resources from that process, okay, so that deadlock no longer exists. But then when we say successfully abort deadlock processes until deadlock no longer exists, successfully preempt resources until deadlock no longer exists. If you need to do this, okay, if you need to do any of this, must be some criteria. Which process I will select first to abort, okay, or from which process I will preempt resources. So there are two ways: either you abort the process or you just preempt the resources, right? But both these steps require some criteria to select the process from which the process which you may want to abort, or the process from where you want to preempt the resources. So for 3 and 4, the selection criteria could be any one of the following, or it can be a combination. So what can be the criteria? Maybe the least amount of processor time consumed so far. It means the process which has executed very small for the very small amount of time. It means it has just started maybe. So in that case, you just abort that process. So there is very less amount of housekeeping job to be done. Or least amount of output produced so far. It means this process has not interacted much with the user and not produced much output required. Most estimated time remaining. It is a reverse part of that. If this process is going to be there for a very long time, because it has to do very much, still it needs to do so much thing. In that case, you can abort that process. List total resources allocated so far. So if you want to preempt resources from any process, then you just check the process in the deadlock state which has least resources allocated, so that you need to do less housekeeping job or with the lowest priority. So all in all, these are the recovery strategies. Either you did abort any deadlock process and you do that until you have come out of that deadlock condition, or you start preempting resources from the processes till deadlock no longer exists. And these are the criteria, some of the criteria that you can use while selecting process for abortion or for the resource preemption. And this is a summary of these three techniques: prevention, avoidance, and detection. So this is just the summary. Whatever we have discussed, it is a summary of that. So you can go through that. And then there is another strategy called an integrated deadlock strategy. Okay. We have seen that none of this technique is efficient technique. None of them is efficient. Of course, there are few problems with detection also, because it is going to abort the process or it is going to delay the process. So in that sense also it is not that efficient. But all this condition, if you check, in certain conditions they are good to go, in certain conditions they are not good to go, right? So can we use some strategy which combines this, all these three whenever required, or according to the situation? Wherever prevention fits, we will use prevention. Wherever avoidance fits, we use avoidance. So we don't use any of this technique as general technique for all. Rather, based on the situation, we can take one of them and use that to solve the problem of the deadlock, right? That is called integrated deadlock strategy. So what it is, as there are strengths and weaknesses to all of these strategies for dealing with deadlock, we have seen that rather than attempting to design an OS facility that employs only one of the strategies, it might be more efficient to use different strategies in different situations. And that is what I'm talking about. So there are one research suggests, okay, one author of the paper suggests one approach. Let us do one thing: group resources into a number of different resource classes. Okay, whatever resources are there, because all these are because of resources, right? This deadlock situation occurs because of resource demand between different processes. So let's group these resources in different categories or different classes. Use the linear ordering strategy defined previously for the prevention of circular weight to prevent deadlocks between resource classes. So now I hope you remember in circular weight, we did the same thing. We had some resource ordering. Here, there is a resource ordering between groups of resources, not between each type of resource. It is between group of resources. And within a resource class, use the algorithm that is most appropriate for that class. So now what we do, we create different classes or the groups of these resources, and between these groups we will use the strategy that we used in prevention by avoiding circular weight, by making sure that there is no circular weight, by applying linear ordering between the resource classes. So that you can use between the group of the resource classes. And within each group, either you can use detection, prevention, or avoidance, whichever is suitable. So this is one example. This is one example of that integrated strategy. Consider the following classes of resources. Now let's consider that all the resources that we have, we put them in different classes, like swappable space. That is nothing but blocks of memory on secondary storage for use in swapping process. I hope you remember swapping in and swapping out idea, which we discuss in process states. Okay, if process gets blocked and there is no free memory, then sometimes we put that block process in the block suspended state. So that suspended state, it is nothing but the swapping. You need to swap that process into the secondary memory. So swappable space is one resource which is in one class. Then process resources like devices, okay, printers and all those devices, so like drives and files and all this, put all those assignable resources, assignable devices in a group called process resources. Then there is a resource related to main memory that is assignable to processes in pages or segments. This main memory concept we will further learn in the next lectures. And then internal resources like IO channels. So now we have created groups, and between these groups there is a linear ordering. Okay, this is the lowest order, this is the highest order, likewise. So I hope you remember circular weight avoidance, how you can break the circular weight by applying linear ordering between the resources. So instead of resources, now we are applying linear ordering between classes of resources. So if any process has acquired any resource from this class, Now it can ask for the resource from this class or this class, but it cannot ask for the resource from this class. That is the meaning. That is the meaning of linear ordering. So the order of the preceding list represents the order in which resources are assigned. And within each class now within each class, which strategy is more suitable? So within swappable space class, prevention of deadlocks by requiring that all of the required resources that may be used be allocated at one time, as in the hold and wait prevention strategy. So swappable space is nothing but the area from the secondary memory, and any process which wants to use swappable space, it needs to claim that swappable space, or it needs to request that swappable space before process starts. So basically it is the idea that we use, that we discuss to prevent hold and wait strategy. So that prevention of hold and wait strategy you can use in this within the swappable space classes. Okay. And also deadlock avoidance can be a possible solution. Process resources avoidance will often be effective in this category. Okay, because this is related to those resources which are normally assigned to processes like app drives and printers and all other devices, right? And avoidance strategy can be a good solution to this problem. Then main memory prevention by preemption appears to be the most appropriate strategy for main memory. So when a process is preempted, it is simply swapped to secondary memory, freeing space to resolve the deadlock. And internal resources prevention by means of resource ordering can be used. Again, some resource ordering idea can be used for internal resources. So this is one idea that in integrated deadlock what is the exact term? Integrated deadlock strategy. They call it integrated deadlock strategy. Basically, it is a strategy to come out of this deadlock problem. So for that, the main idea is, first of all, classify all the resources in different groups and apply linear ordering between those groups. And within each group, apply any suitable strategy out of deadlock prevention, deadlock avoidance, and deadlock detection. That is the bottom line. And finally, there is one classical problem called dining philosopher problem. That is what we are going to discuss. Okay, with this problem, we will see how deadlock happens and how we can solve that deadlock. So what is the problem? Devise a ritual, basically algorithm, that will allow the philosophers to eat. Okay, now let's understand what is the total setup of this problem. There are 5 philosophers. They are doing only 2 things in their life: thinking and eating. Okay, and they only eat spaghetti. Okay, they only eat spaghetti. That is their food. So they do only 2 things in their life: either they are thinking or they are eating. And to eat spaghetti, they require 2 forks. And there are total 5 such philosophers. And on the dining table, you can see there are chairs for 5 philosophers. There are 5 dishes. So these resources are enough. Each philosopher can have his dish or his or her chair. But then if you see how many forks are there. So again, forks are total 5 forks are there. But one philosopher needs to use 2 forks to eat the spaghetti. Okay. So it is not possible that all these 5 can eat at the same time. Right. So what is the problem? So you need to find an algorithm that will allow the philosophers to eat. No 2 philosophers can use the same fork, that we know, at the same time. That means mutual exclusion is required. Okay. For example, if there are 2 philosophers here and here, they cannot use the same fork. That is not possible. So mutual exclusion is required. No philosopher must starve to death. That means avoid the deadlock and starvation. It means, suppose the worst condition, let me show you the worst condition. Suppose all five philosophers feel hungry at the same time. So they sit here on their chair and all of them have already take one fork, right? They have taken one fork, which was on their left side, let's say. So P0 has taken this fork is taken by this philosopher, this fork is taken by this philosopher, and so on. So all these philosophers have one fork, but they require 2 forks to eat. No philosopher in this situation can eat. And basically they will starve, literally starve, as they cannot eat. And there is a deadlock. Because no one can release no one releases their fork until and unless they complete their eating. But to complete their eating, they require one more fork, which is not going to be there. So that is the deadlock problem. So you need to devise an algorithm which allows mutual exclusion as well as it is not allowing deadlock to happen. So how can we do that? So this is one solution using semaphore. Okay, let's say there are 5 forks. So there are 5 semaphores. We call it fork, right? And initially it is 1 because all forks are available. So you can see that main process, what it does, it creates this philosophers from 0 to 4. And this is the process, this is the code which is executed by each philosopher. So basically it is an infinite loop. And as I told you, they do only 2 things, think and eat. While thinking, there is no problem. They can think independently. But while eating, they are using shared resource called fork. So you can see, first, let's say they are thinking, but now they feel hungry, so they want to eat. So they need to wait for their fork. So if philosopher 0, first it will wait for fork 0. That is on the left side. You can see that. P0 waits for fork 0. That is on the left side, right? And then it will go for fork 1. So first wait for fork 0 and then wait for fork 1. 1 means I plus 1 more 5. That will give you the proper solution because philosopher 4, philosopher number 4, this is philosopher number 0, let's say. Then it is waiting for fork 0 and fork 1. But if it is philosopher 4, number 4, then it is waiting for fork 4 and 4 plus 1, that is 5 more 5, 0. So left and right both basically. So first wait for left fork, then wait for right fork. And if both are available, then you can eat. And after eating, you release those forks. First, you will release right fork and then you will release left fork. So this is the simplest solution, which allows for no deadlock and there is a mutual exclusion also, right? Now, why it is allowing, let's say all these philosophers are there. All these philosophers are there, okay, at the same time, suppose. But what is happening here, if anyone has waited on this fork I, it is also immediately it is getting the another fork, right? And then only it can start eating. Now the here, okay, one more thing. So what is the problem? Okay, can you see any problem? First of all, we need to devise an algorithm which achieves 2 things, mutual exclusion and it avoids the deadlock, or it makes sure that there is no deadlock. Does this algorithm guarantee mutual exclusion? Yes, it guarantees mutual exclusion because before using fork, you need to wait on that. So mutual exclusion is guaranteed, but there is no guarantee of no deadlock. Deadlock may happen. How it is possible? Let's say all 5 are there seated on the table. P0, first it executes this fork 0. Maybe it is granted because it is free. So it is granted, but then process gets switched and philosopher 1 executes. And it is going to ask for fork 1. It is granted. And let's say process 2, that is philosopher 2. So all of them, if they get 1 fork, and in that sequence, this process gets executed, it means all philosopher, they have lifted their left fork. So there is no more extra fork which can be given to any other philosopher. And that is how deadlock is possible in this. Mutual exclusion is there, but there is no deadlock. There can be a deadlock with the help of this algorithm. So how can we avoid deadlock? So one solution is, don't allow all these 5 philosophers to sit on the chair at the same time. Don't allow 5. At max, allow only 4. At max, allow only 4 philosophers. How it helps? If you allow at max only 4 philosophers, it is guaranteed that at least one of them can get 2 forks and complete their eating, and then release all those 2 forks, and then allow another philosopher enter into that, or allow them to sit on the table. So here, rather than table, we call it a room. Let's say dining room. Okay. So if any philosopher wants to eat, first it needs to go through this room. There is a semaphore, and there are only room for the 4 philosophers only, not 5. Not all 5 can enter into the or can sit on the chair. Only 4 can sit. So this is a room for 4 only. So you wait for, so let's say there are 4 philosophers, all 5 philosophers want to eat, but only 4 of them can cross this particular point. Only 4 of them can cross this particular point. Even all those 4 has lifted their left fork, still one more fork is left. It is still there, and which can be acquired by one of the philosopher. And then they eat and then signal both the forks and then signal room. So one more philosopher can still enter, because still there are 3 philosophers. So one more can enter if he or she wants to enter. So this algorithm definitely it guarantees mutual exclusion plus deadlock avoidance. And this is the solution using monitor, which is very similar to the previous case. So let me go through this solution also. So you can see that the main process is this philosopher process. What it does, it think, and then whenever it philosopher wants to eat, first it will get forks, and get forks, it means simultaneously it is getting both the forks. So when one philosopher is getting a fork, it is a process from the monitor. Get forks is a procedure from the monitor. Get forks is a procedure from the monitor. And I hope you remember, when anyone is executing one procedure from the monitor, no other process can enter into the same monitor. So automatically, when one philosopher is trying to get the forks, it will get both the forks at the same time. So no other can disturb it. And then eat the spaghetti and release the forks. Again, release the forks is nothing but the procedure from the monitor. So if someone is executing release forks, at that time no other philosopher can enter into this monitor. And this get forks will help you to solve this problem, because while one philosopher is executing get forks, no other philosopher can execute at the same time. And because of that, both the forks will be acquired first, and then it will start eating. So this is the solution to dining philosopher problem with the help of monitors, and this will ease out your problem. So one solution is this. This allows only 4 philosophers at the time on the dining table. There is no such restriction here. But then in this case, what happens? Whenever any philosopher is trying to get the fork, he will get both the forks at the same time. And while it is getting the forks, it cannot be disturbed by other philosopher. Okay, and that is how it is possible to solve this problem. So with the help of this, finally we have completed this chapter. I forgot the chapter number. Maybe it is chapter number 6 or 7. So we are done with this. Sorry, it is chapter number 6. So we are done with chapter number 6. With this, process part is completed. And by looking at your interest, now I am not going to start anything new right now. I'll stop here, and we will continue with the next topic in the next lecture. And if this is how you are going to participate in this lecture, we will be able to quickly finish all these lectures, and you need not to spend any extra time for that. Okay, so it is good for you if you want to go this way, and it is also good for me. I need not to spend more time. I need not to spend any extra time for this. Okay, and if you have any query or question, I am giving you some time right now. If you have any question or query, you can ask. Otherwise, we can end this session here. Okay, so I assume that there is no question. Should I assume that? Fine. Samir says there is no question. Okay. In that case, let's end this session here. And now you are free before half an hour, right? I mean, it's good for you. Go and enjoy your Diwali. Let me complete this.